Okay, so today we are going to learn how to take a spectrogram of a human speech recording and actually understand what a person was saying on this recording only by looking at the spectrogram. We've done this research on our speech enhancement project, and the idea was to understand which spectrogram parameters are better to feed it to a speech denoising model. But it turned out to be an interesting topic in general. It is on kind of a crossroad between signal processing, linguistics, and even physiology. So I hope that today's presentation would be interesting. And as you might have noticed, I have a small script that builds a real-time spectrogram of my speech. So hopefully this will make our today's discussion a bit more interactive. Technically, it would be interactive only for me, but I hope it at least will make it a bit more interesting. So let's start. To learn to understand words from the spectrogram, we need to start with separate sounds. And we will start with vowels, which are sounds like a, o, u, e, and others. For this, we first need to learn about a popular model that is used to represent human speech, and this is a so-called power source filter model. Uh, Power here stands for lungs, which produce the airflow. Source are our vocal cords that are indeed a source of all vibrations in the speech, and filter is our vocal tract, which is this whole part, the throat, mouth, and the nasal cavity. But more commonly in this field, we are working with just source filter model, so we forget about lungs for some time, and we can see it in more details. So our source, our vocal cords produce vibrations in a form of harmonic waves. These waves are the same for every sound, and they only differ depending on the pitch of the voice. So if you try to speak with a higher pitched voice, you'd get a higher fundamental frequency here. Where the difference between sounds comes is in the filter. So we see this curve, the frequency response of the filter, which tells us which frequencies are either suppressed or amplified by the filter, and it is different for each sound. So depending on it, we might hear a different vowel. And I think it's the first time when we can go back to the spectrogram and do some practical exercise. So now I'll try pronouncing some vowels and we will then compare them. A, E, O, U, E. Okay, that's it. And as you can see, I haven't lied to you. Indeed, we have all the same harmonic waves for each of the vowels, even though they sounded completely differently. And the only way to distinguish them is actually to see which harmonics were suppressed by the filter. So at this point, we could already tell the vowels between each other just by saying which of the harmonics were left visible on spectrogram and which were completely removed. However, this is not very reliable way to do this. As you can see, vowels like a and look quite similar. If we think of them just in a way of which harmonics are visible, so we can actually do better. If we get back to our spectrogram, we can see our presentation. So we can see that the frequency response of the filter has certain peaks. These peaks are called formants and denoted like this, F1, F2, F3. And it turns out that location of these formants is pretty unique for each vowel. So we can distinguish them just by the formants. And even more than that, we only need first two of these formants to distinguish vowels reliably. I think we'll need to have a quick dive into the math behind this. So this filter is actually a simple linear filter, which means that for a filter of order p, we would have p coefficient and we would calculate a current sample of our recording as a sum of p previous samples weighted by coefficients of the filter. So indeed a very simple model. And when we already have a speech recording and we want to recover this filter to later find formants on it, we need some way to determine these coefficients. Actually, you could just solve this as a least squares problem, but there is no need to do this manually. For Python, you can use the Librosa library, namely the LPC function, which stands for linear predictive coefficients, exactly what we need. So it will give us p coefficients, and then you can reconstruct the frequency response curve using the freqz function from SciPy. Okay, so now we have the curve. It's good for visualization, but we need actual formant values. And there are two ways to get them. The first is easy one. So you literally find peaks of this curve. You can use SciPy find peaks for this. But unfortunately, this in some cases is not very reliable. So peaks might not be pronounced enough to be detected by the function. So if you need to find values reliably, you should take a bit longer road. Namely, you would solve a polynomial defined by the coefficients of the filter. You can just use NumPy roots for this. And this would give you a set of complex roots. You can think of them as candidates for your formants. From these complex values, you can calculate frequency and bandwidth of each candidate, and then threshold them to pick a final set of formants. That's obviously a very brief explanation of this. If you want a more detailed tutorial, go to this post on MATLAB site. And no worries, even though I haven't touched MATLAB in my life, it still was pretty straightforward to port this to Python, so great tutorial, highly recommend. But anyway, now we know how to get the frequency response, and we know how to find formants in it, and let's see what this actually gives us. We have two example vowels here, A and E. Orange curve here is the original spectrum obtained with Fourier transform, and the blue curve is the frequency response of the filter. And if you scale it properly, it actually forms some kind of an envelope around the spectrum, and that's why in literature it often referred as spectral envelope. And on this envelope we can easily find first two peaks, being first two formants, and indeed we see that their positions is very different for A and E. I think we can check this out for all formats. For this we will go back to our small script. And lucky enough, it has a special mode in which it shows us the spectrogram built out of envelopes rather than source spectrum. And we can see different peaks here being our formants. And indeed, for all sounds that I've pronounced, they are located differently. So you could distinguish them. I actually have a small screenshot in the presentation too of roughly the same experiment, and we will use it later for our practical exercise. There is one important thing to note is that for predicting filter coefficients, you need to set a specific filter order that you want. And you need to pick it carefully, because if you set it to a low value, your envelope would be too approximate, and you would get incorrect formants. In the same way, if you set it to a very high value, your envelope would follow the original spectrum too precisely, and you would get some noise peaks that would also give you incorrect values. There are different recommendations of how to pick the filter order. Mainly, they say that you should set it twice as high as the number of formants that you want to be detected. However, I don't find this advice very helpful, because at least it doesn't account for the sample rate. And in practice, I found that a very simple way to pick P is to just take your sample rate in kilohertz. So if you have a 16,000 hertz sample rate, you would have a filter of order 16, and this works pretty well. Though if you would do similar experiments yourself, I still suggest to always double check that you are getting nicely looking envelope and correct format values. And now it's time for a part that I've promised about physiology. We'll start with a more simple example. So our tongue forms a so-called constriction in mouse. In this picture, it doesn't look like much of a constriction, but we still consider it to be there. And it separates our vocal tract into two parts. First is the pharyngeal cavity, so basically our throat, and the second is oral cavity, so basically our mouth. And if we see how we pronounced vowel E, we have a very large pharyngeal cavity, which results in a very low value of the first formant, and a very small volume of the oral cavity results in a very high value of the second formant. On the other hand, when we have sound A, volumes of the two cavities become closer to each other, and we also see that formants move closer to each other along the spectrum too. So that's quite a nice connection, but actually it goes even deeper. There is a set of vowels that are called cardinal vowels, and these are such vowels that are pronounced with an extreme position of the tongue's highest point. You can actually see some diagrams here. You see the tongue's highest point denoted on each of them. And when we are pronouncing each of the vowels, this point goes around this trapezoidish figure. And we actually have this figure in a larger scale too. And interesting thing is that if we plot a scatter plot of cardinal vowels with first two formant values being its axis, we would see a remarkably similar figure. So it's not exactly the same, and that is mainly because tongue is not the only thing that influences how vowels sound, but still the similarity is quite impressive. And I in general find it very curious that we have kind of complex model like human voice tract and a very simple mathematical model that just has a linear filter, and yet it gives us such good connection between them that we can even recover a position of the tongue just from formant. So I think that is really curious. And for the vowels, that's pretty much all. We have a couple of conclusions to make. First, that we need a high enough frequency resolution of the spectrogram so that we could distinguish different harmonic waves and formants. Though in practice, it doesn't mean that you should take as high frequency resolution as possible. Just reasonably high would be enough. And also that actually formants gives us a pretty good classifier of different vowels, and if we have formants, we don't need anything else. Of course, there are some other interesting features of vowels. For instance, we haven't touched diphthongs in this presentation, which are vowels like I, probably being the most popular one, but I think it's a more advanced topic and we can actually do without them today. So now we'll go to consonants. These are sounds like B, N, P, T, and others, and we can go back to the spectrogram again. So for studying consonants, it is better to pronounce them between two same vowels, like this. Apa, aba, ata, ada, asha, aja. And with consonants, we cannot do as precise classification as with vowels, but what we can do is actually separate them in two groups in different ways and say to which group the specific consonant belongs. And one of the most obvious things is voiceless and voiced consonants. So voiceless ones are like p, t, sh. They are pronounced without vibrating with vocal cords. So in our power source filter model, we remove source and only have power and filter. And on the spectrogram, we see a portion of silence in such consonants, so all harmonic waves that were in nearby vowels are fully interrupted and we have the full silence right here. On the other hand, voiced consonants involve some vocal cords vibration. It's consonants like b, d, j, and others, and we indeed see that at least some of the harmonics are still preserved. Okay, that's the one thing. And you might have noticed that I've lied a bit about the full silence and that two last consonants have some noise in between vowels. And that's actually useful for another classification. So basically dividing them into fricative and non-fricative consonants. So fricative consonants like sh, j, s, z, h, and others would have that noise. And actually that noise is pretty unique for each of them, and we can even classify them by it. And non-fricative consonants obviously do not have some noise, do not have such noise. And I'm sorry, I'll have to interrupt for a minute because I forgot to connect my laptop to power. Okay, now we are saved. And let's go to the next one. And another interesting things are trilled consonants. I would say the best example is R. There are actually trilled versions of other consonants like B, but I won't even try to pronounce it. So let's just try this R. Arra. You can probably see some pattern even on the basic spectrogram, but it's actually much better observed in the envelope one. Let's switch to it. And you can see very pronounced vertical lines here. And actually, even if I pronounced R quite briefly, we will still see the similar pattern, like this. Ara, ara. Yeah, so you can see that some vertical lines are still appearing. And probably the last thing that I'd like to show are nasal consonants. So these are n and m. Let's compare them with non-nasal ones. Abba, aga, anna, amma. First of all, you could immediately see that nasal consonants have much more harmonic waves preserved than non-nasal ones. And the difference is also obvious on the envelope spectrogram. You see that here envelope kinda extends much longer along the frequency axis to higher frequencies compared to non-nasal consonants. You can see that there is some difference between N and M, but it's actually not very reliable. So if we see something like that, we can say that it's either N or M, but we cannot classify them precisely. Okay, I think we can go back to our presentation. Here we have some slides with the things that we've already seen. So that is a classification of voiceless and voiced fricatives, and we have here all the fricatives, so we can use that later as a reference when we will try to determine fricative by its noise pattern. Nasals, trilled, and now we will have a couple of slides with things that are not very reliable, so I won't waste time to try to show them in practice, but still maybe it's useful to know about them. So these two are a sound V like in vowel and R like in result. Both of them do have this V-shaped pattern that they create in formants in the envelope spectrograms, but unfortunately you cannot always see it very clearly, so cannot rely on it too much. And another one are plosives like P, T, K, and what they should do in theory is create a so-called burst, which is a narrow vertical line of noise after them. And on this particular spectrogram, I was able to get it, but this also very unreliable. More often you won't get it. So if you see something like that, you can make a guess that this is one of the plosives. But if you don't see the burst, you cannot be sure that the consonant is not a plosive. Okay, so some conclusions. Unlike with vowels, we don't have specific criteria like we had with formants. So we have to do this division into many pairs of different types of consonants, and by understanding to which types the particular consonant belong, we can actually make a guess which consonant is this. We need a high enough resolution along the time axis to be able to see some patterns, and that would be especially useful when we get to reading words, because in actual speech sounds are pronounced much more briefly, and especially consonants, so a good resolution is useful. And unlike with vowels, envelope spectrograms with formants and all that stuff is not necessary, but is still useful for certain features. And now we can have, I think, the most fun part is actually some practice. I have this spectrogram here, and we will try to understand what word was pronounced on this recording. This spectrogram has a very high resolution along the time axis, so don't be surprised that some patterns would look a bit stretched. That is necessary to distinguish all sound when we have an actual speech. And what I would start with is identifying vowels. So I would say that vowels are those segments of the spectrogram, the envelope one mainly, in which we can consistently see first two formants. So these are these three segments. And we have our reference here. So if we start with the first segment, we see that first two formants stand quite far from each other, and the first one being at quite low frequencies. And among all the available examples, the only thing that matches this pretty well is the E. And actually, if we look at the last one, even though it's pronounced more briefly and thus less clear, its formants are located almost exactly the same as in the first one, so that is also probably E. Now the middle one, we also have two formants that are located not too close to each other, but closer than with E. So probably that is not letters or letter sounds like R or O, because they have formants very close, or even U, where they are just barely distinguishable. Thus, I'd make a guess that here we have E. Okay, now we're done with them. And another thing that we might notice is that this word have three fricatives, so we can continue with them. Let's, I think, start with the middle one, because it's the only one voiced among them. We can determine this by the presence of some harmonics and actually also by some formants that are visible on the envelope spectrogram. And another characteristic thing about it is that the amount of noise is actually pretty low. So if we check all the voiced fricatives, like V, Z, Z, and J, we can see that the lowest amount of noise is characteristic of the V fricative. So I would say that we have V here. Now let's go with the voiceless ones. The first one also doesn't have that much of noise, and it has a relatively low amplitude. So I would actually look at the F sound, and I would guess that we have it right here, because others have much more noise. And the last one. So here we have a quite substantial amount of noise. I would say that this is either S or Sh. However, we can see that Sh has a lot of high amplitude noise. It's almost as bright on the spectrogram as nearby vowels. We don't observe this here, so that is most likely S. And now we have some more consonants left. I think one of the most obvious ones is this one. That is what we've already seen. That is one of the nasal consonants, and we can determine this by a lot of harmonic waves left here, or by an extended envelope curve right here. As I mentioned, we cannot tell for sure whether it is N or M, so we would have later guess which one of them we have here. This one, it also might look as a nasal one, because we also have an extended envelope. However, you might notice here one vertical line, which is actually more pronounced on the basic spectrogram. So because of this, I'd make a guess that we have R here. And now we have the last one, and this is actually a complicated case because I cannot tell for sure which one is this. It is surely a voiceless consonant, and it is for sure not a fricative one because we don't have a lot of noise. So this narrows at least down a little bit, but we still have to do some guessing or brute force search. So that's what our final results look like. We have two options here and some options here. Though we were able to throw away some options like fricatives, we still have to iterate through multiple of them. So if we cannot guess the word already, we can just try out different combinations. So probably something like frequency or frequency doesn't sound as a thing. But eventually we will come up with an option frequency, and this is indeed a correct answer. So hooray, we've done this. Obviously, this is not a very fair experiment because I knew what the word actually is, so I knew what to look for. On the other hand, I'm also not very experienced with this, so if you ask a person with more experience who knows more patterns of a specific language and has more skill in finding them, I think probably just taking a spectrogram and reading it like a book still won't be possible, but I think such person would be able to make a lot of cool educated guesses and tell us a lot of interesting things about the speech recording just from the spectrogram. Okay, so I hope that was at least a bit interesting, but you might ask what is actual use for this information. First of all, that's what you're doing this research for on the speech enhancement project. That is first to understand which parameters of the spectrogram would make speech more distinguishable. And so this spectrogram could in theory allow to train a better model. And it actually is also useful to analyze your model that outputs some speech. So maybe it's speech denoising model or speech synthesis model, because metrics like mean error or even more advanced like PESC could tell you that there is something wrong with your model, but they cannot tell what exactly is wrong. You can listen to outputs of your model and probably hear that something is not all right, but that also doesn't give you a very specific understanding. So examining spectrogram, knowing what you expect certain sounds to look like and what you actually see outputted by your model could be a useful thing. And finally, the linear predictive coding. This is like this whole process of modeling the speech with the linear filter is used in many approaches for voice compression. Such algorithm was actually in earlier versions of GSM for speech synthesis, speech encryption, audio codecs, and many others. In many of them, this is not state of the art, so it's more like a classic approach, but it's still good to know some classics even if you are not going to work with them directly. Okay, here we have some conclusions that I probably won't repeat because we've already heard all this. And yep, that's all. Now I can answer your questions